All right, welcome. Today, we're diving into the world of thermodynamics. Now, I know that word sounds kind of heavy, but at its heart, it's really just the science of energy, how it moves, how it changes, and how it powers literally everything. Let's get into it. So that brings us to the big question, right? Think about it. The engine in your car, the power plant that lights your home, even the metabolism happening in your own body right now. It's all about energy flowing from one place to another. But how in the world do we describe that? How do we predict what it's going to do next? Well, it turns out, to answer that, we need to learn a whole new language. And just like learning any new language, you can't just jump into writing poetry. You've got to start with the absolute basics. Before we can even begin to analyze energy, we need to agree on what it is we're actually looking at. So, first things first, let's lay down some ground rules.
Okay, so the very first thing you have to do is define your system. I want you to think of it like drawing an invisible box around the one thing you care about. That box could be around the coffee in your mug, or the engine in a jet, or even an entire star. Once you've drawn that box, everything else, and I mean everything else, in the entire universe is just called the surroundings.
Okay, so we've got our box, but now we have to ask a really important question. What can get in and out of it? Can stuff cross the walls of our box? Because the answer to that question puts our system into one of two major categories. And this right here, this is the basic setup for everything we're going to talk about. You've got the system, that's the star of our show. You have the surroundings, that's everything else. And that dotted line separating them, that's the boundary. Seriously, every single problem in thermodynamics starts with this simple picture.
Now, let's look at our first type of system, a closed one. See how the arrow for energy can go in and out? You can heat it up, you can cool it down, but the arrow for mass is blocked. Nothing physical can get across that boundary. The perfect example is a sealed can of soda. You can put it in the fridge, but the soda itself isn't going anywhere.
And then you've got the opposite, an open system. Here, the doors are wide open. Both energy and mass can come and go as they please. An air compressor is a great example. Air, which is mass, is constantly flowing in and out, and so is energy in the form of work and heat. And honestly, most of the things we deal with every day, yeah, they're open systems. All right, so we've picked our system. We know if it's open or closed. What's next? Well, how do we actually describe it? Like if we could freeze time for just a single moment, what would we measure to capture a perfect snapshot of its condition?
That snapshot, that's what we call a state. And a state is defined by its properties, things we can actually measure, like its temperature, its pressure, or how much space it takes up, its volume. You tell me those numbers and boom, you've perfectly defined its state at that exact moment.
Now these properties, they actually come in two flavors. First, you have intensive properties. These don't care about how much stuff you have. The temperature of the coffee in your mug is the same whether the mug is full or half empty, right? Then you have extensive properties, which absolutely depend on the size. The total mass or volume of your coffee is definitely different if the mug is half empty. It sounds simple, but trust me, knowing this difference is super important later on.
But let's be real. Things don't just sit still, do they? Systems are always changing, always in motion. And that change, that journey from one state to another, that's what we call a process. It's the action part of thermodynamics.
And check this out, because this is a really cool way to see it. On the left, you've got a real thing, some gas trapped in a cylinder. It has a real pressure, a real volume. Now look to the right. We can represent that entire physical thing as just a single dot on a graph. That point, state 1, is our snapshot. We've just turned a real object into a piece of data on a map. So when that piston actually moves, the gas is going through a process. It's moving from its starting point, state 1, to some endpoint, state 2. And the line you would draw connecting those two dots on the graph, we call that the path. It's literally the journey the system took. But not all paths are created equal. On the left, imagine you just yank the weight off the piston. It explodes upward in a chaotic mess. The change happens so fast we have no idea what the path looked like. It's just a blur. But on the right, what if you remove the weight 1 grain of sand at a time? The piston would rise super slowly. This perfect slow-motion change is called a quasi-static process. And it's useful because we can actually draw a solid line from start to finish. And if you can draw a line, you can use math on it. That's the key. Okay, that was a lot of theory. Let's bring this all back down to earth for a minute and talk about one of the most important properties we can actually measure and feel: pressure. So pressure sounds kind of scientific, but the basic idea is actually super simple. It's just a force spread out over an area. Think about the air inside a balloon.
You've got trillions of tiny air molecules zipping around, constantly crashing into the inner wall of that balloon. All those tiny little collisions add up to a big push, and that collective push is what we feel as pressure.
Now, here's a number you should probably tuck away in your brain. 101.325 kilopascals. What is that? Well, that's the standard pressure of our atmosphere at sea level. It is literally the weight of the entire column of air stretching from your head all the way to space, pressing down on you. We use it as a reference point all the time.
Okay, this is a really, really important point. There are two ways to talk about pressure. Absolute pressure is the true total pressure, measured up from zero, a perfect vacuum. But what your tire gauge measures is gauge pressure. That's the pressure above whatever the local atmospheric pressure is. So if your tire gauge reads 32 psi, the true absolute pressure is actually that 32 psi plus the 14.7 or so psi from the atmosphere pushing on the outside of the tire.
So, that's all great in theory, but how do we actually walk up to something and measure this stuff? What are the tools for the job?
Well, one of the oldest and cleverest tools is the manometer. It's literally just a U-shaped tube with some liquid in it. The pressure you want to measure pushes down on one side, and the atmosphere pushes down on the other. The liquid gets pushed up, and the difference in height, that little Z you see there, that directly tells you the gauge pressure. It's so simple, but so smart.
But, for a quick and easy reading, you'll probably see something like this, the Borden gauge. You've definitely seen these on bike pumps or air compressors. Inside, there's a little curved, hollow tube. When you pump pressure into it, the tube tries to straighten out. That tiny movement is connected through some gears to the needle on the front, giving you an instant reading. Just a brilliant piece of mechanical engineering. All right, let's do a quick recap of the core ideas, the absolute essentials. First, you define your system. That's what you're studying. Then you describe its state at any given moment using its properties. The change from one state to another is called a process, and we took a closer look at pressure, which is one of those key fundamental properties you can always measure.
So, we've just learned the basic vocabulary and grammar for the language of energy. We know how to define things, how to describe them, and how to track their changes. But what are the rules of this language? What are the unbreakable laws that every single system and every single process in the entire universe has to obey? Now that is where things get really interesting. But that's a story for another time.